So next round of errors or chopping error. Numbers such as pi, e, and the square root of 7 cannot be expressed by a fixed number of significant figures. Because computer use a base 2 representation, they cannot precisely represent certain exact base 10 numbers. So ito yung sinasabi ko, conditions lang ang kayang i-show or ang kayang i-represent and kayang i-store ng ating computer. Kasi ang ginagamit nilang system ay binary system. While ang ating calculation or some of the numbers presented or some of the data presented are in base 10 numbers or yung ating decimal numbers. Therefore, they cannot be represented exactly by the computer. In addition, the discrepancy introduced by the omission of the significant figure is called round-off error or the chopping error. For example, so we have here pi 3.14, 15, 92, and so on and so forth. During calculation, if the value used is 3.14 or 3.1416, then a round-off error occurs. Therefore, round-off error is rounding off the value that cannot be expressed by the fixed number of significant figure. Number system is merely convention for representing quantities. Because we have 10 fingers and 10 toes, that number system that we are most familiar with, the decimal or the base 10 number system. So the base 10 number system uses digits from 0 to 9 to represent numbers. So we have here numbers on the computer are represented with a binary or base 2 system. So it is more understandable kapag in-explain natin itong ating figure 3.5. We have here the decimal value. So 86,409. So paano siya inire-represent or paano nakakalculate in terms sa base 10? So base 10, 10 raised to 0 is simply equal to 1. So 9 times 1 is 9. And 0 times, so ito naman ay 10. And this one is 100, 1,000, and 10,000. So ito yung ating representation ng decimal or base 10 system. Ang pinagkaiba niya sa ating binary, which is using the base 2 system. So if we had an example of 10101101, so using a base 2 system, for the 2 raised to 0, it will be equal to 1. 2 raised to 1 is 2. This will be 4, 8, 16, 32, 64, 128. For base 2 at 0, so may value siya na 1. So that would be 1 equals to 1. For 0, 0 times 2 is equals to 0. So on and so forth. And summing up, so this will be the represented number. And this number is a decimal number. Hindi na natin masyadong elaborate to kasi ito ay yung computer fundamentals in programming. So, signed magnitude method is the most straightforward approach that employs the first bit of a word to indicate the sign with 0 for positive and 1 for negative. The remaining bits are used to store the number. For example, the value is negative 173 and would be stored in 16-bit computer system as shown in figure 3.6. So take note class, ito yung ating 16-bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Kaya siya 16-bit. And the first part of that bit system will be for the sign and this will be for the number. So, if we have the value, so using yung ating previous data, using this data, the 10, 10, 11, 01, 10, 10, 11, 01, which has a value of 173, and 1 is for negative and 0 is for positive. So, dahil negative 173 yung i-store natin, so we will have here a 1 value. So, meron siyang AD display or the decimal integer will be negative 173 in 16-bit computer using signed magnitude method. Floating point representation so typically represents fractional quantities in computer. In this approach, the number is expressed as fractional part called mantissa or significant and an integer part called length or characteristics. As in m times b raised to e. M is the mantissa and b is the base of the number system being used and e is the exponent. For instance, the number 156.78 could be represented as 0.15678 times 10 raised to 3 in floating base 10 system. Figure 3.7 shows one way that floating point number could be stored in one word. So, in this manner, the first bit represents sign. The next series bits will be for the signed exponent. Next would be for the mantissa. For example, 1 over 34 is equals to 0.029411765 was stored in a floating point base system 10 that allows only 4 decimal places to be stored. Thus, 1 over 34 would be stored as 0.294 times 10 raised to 0. The inclusion of the useless 0 to the right of the decimal forces to drop the digit by 1 in the 5th decimal place. The number can be normalized. So, pwede nating i-normalize yung number by removing the leading zeros. By multiplying the mantissa by 10 and lowering the exponent by 1, going to use 0.2941 times 10 raised to negative 1. Makikita mo na ang representation niya is simply this mantissa, the base or the base 10, and for the exponent. Thus, we retain an additional significant figure when the number is stored. The consequence of normalization is that the absolute value of m is limited, that is 1 over b is less than or equal to m less than to 1, where b is the base. So, for example, base 10 would range from 0.1 to 1, and for base 2 system, would range from 0.5 to 1. Floating point representation allows both fraction and very large number to be expressed in the computer. So, base system limits on what can be stored and what can be represented. Going back to our previous example, so we know that the value of pi is 3.14, so on and so forth. So, if we round off or chop to 7 significant figures, we will have here the round off error kasi nag-chop off tayo. And doon sa 7 significant value, yung magiging value ng iyong pi will be 3.141592 kasi nasa 7 significant figures. And finding the round of error or E sub t will be equal to the true value minus the approximated value over the true value multiplied by 100%. This is the true value. This is the approximated value based on the 7 significant figures. True percent relative error will be 0.0002%. So, i-round off naman ay let's say 3 significant figures. So, pi will be equal to 3.14. So, ang ating epsilon sub t will be 0.05%. The more na nagkaroon tayo ng lesser na significant figure kasi nag-chop off tayo, the more na mas malaki yung percent error natin. For example, the derivative of the function 1 over 1 minus 3x squared is given by 6x over 1 minus 3x squared squared. So recalling yung ating calculus or the differential calculus, so following the du over dv, so this would be v du minus u dv over v squared. 1 3x squared, derivative of 1 is 0, minus 1 times, derivative of this is negative 6x, and divided by v squared, so 1 minus 3x squared squared. Simplifying, we will be able to have 6x squared, 1 minus 3x squared squared. After calculating the first derivative of the function, do you expect to have difficulties evaluating this function at x equals to 0.577? So, try using 3 and 4-digit arithmetic with chopping. So, magkakaroon tayo dito ng calculation ng ROE or yung ating round off error. So, this is an example in finding the round off error. And we have here two situations. We have the 3-digit arithmetic with chopping and the 4-digit arithmetic with chopping. And we have a value of x equals to 0.577. So, in this problem, try calculating this using Excel. Getting back sa ating Excel, so ang ginamit kong ulit ay yung dati natin na ginagamit na Excel file. Getting back doon sa ating dating Excel file, in this particular sequence class. So, meron tayo ditong value ng ating x. Ito yung ating given. And this true value is from the equation 6x, 1 minus 3x squared squared. We can simply define this para mas makita nyo. So, palitan natin. X, 3x squared squared. So, this is the true value. And meron tayo, the first situation, we have here the 3-digit significant figure. ROE or chop. Hahanapin natin yung ating chop value. And for the true value from the first derivative. So equate lang natin siya dito. Kasi pareho din naman yung ating gagamitin. And ito yung ating function. About the first derivative of the function. So this is the true value. Wherein x is equals to 0.577. So, hinati-hati natin yung ating values from x, 6x, x squared, 3x squared, 1 minus 3x squared. Para mas maunawaan nyo kung paano na-calculate. So, the value of x is simply x. 6 times x. Then, we have here x squared, 3x squared. Ayun, nakalimutan ko yung ating multiplier. And the 1 minus 3x squared. From this, what would be the chop value? So, from here, class, using the 3 significant figures, so the value will be 3.46. Yung ating x squared will be 0.332. Hindi tayo nag-round up, just chopping off. For the 3x squared, ang pinagkaiba ng 3x squared class, ang gagamitin na natin would be 3 times this value as x squared. And for the 1 minus 3x squared will be this particular value. So, dito class, gamit yung ating chop value, ano na ang magiging value ng ating derivative of the function of x. That would be 6x divided by 1 minus 3x squared squared. So, meron tayong makukuhang value of 216,250. So, napakalayo ng ating value sa ating true value for the 3 significant digits or arithmetic chop off. So, galing dito, we're going to find what would be the error. So, simply using true value minus approximate value all over approximate value times 100. True value minus approximate value divided by true value times 100. Because of the chop value, ang ating error ay nasa 90.81%. For the second situation, the value of x, simply x, or let's just copy this out kasi yung ating result dito ay pareho lang ng mga result dito. And the difference, sabi dito, 4 significant digits. So, ang magagamitin na natin ay 3.462 and 0.3329. With this data, same process. So, 3 times x squared Don't forget, pinag-squared na natin to. So, hindi na kailangang i-squared pa. So, be careful ng mga processing. 1 minus 3x squared. Same process. Kunin din natin yung magiging first derivative of the function of x na chop value na. So, meron tayong 6x divided by 1 minus x squared raised to 2. 1 minus 3x squared squared. So, yung magiging value niya will be 2,048,521. So, kunin ulit natin yung round of error. Ang magiging value niya will be true value minus approximate value divided by true value times 100%. Makikita niyo dito, class, na 14.86% yung ating makukuhang percent ng ating error. So, ibig sabihin, class, the more significant figures are used, the more accurate the approximate value to true value, or the lesser the round of error. So, lesser yung round of error natin dahil marami yung ating significant values. So, especially kung yung mismong buong true value yung ginagamit natin sa calculation para ma-avoid natin yung round of error. Continuing with our discussion, so we will now move to truncation error. So, truncation error are those that result from using an approximation in place of an exact mathematical procedure. In order to gain insight into the properties of such error, we now turn to a mathematical formulation that is used widely in numerical methods to express functions in an approximate fashion, the Taylor series. Taylor series provides a means to predict a function value at one point in terms of a function value and its derivatives at another point. In particular, the theorem states that any smooth function can be approximated as a polynomial. A useful way to gain insight into Taylor series is to build it term by term. For example, the first term in the series is the function of xi plus 1 is equal to or congruent to the function xi. This relationship, called zero-order approximation, indicates that the value of the function at the new point is the same as its value at the old point. This result makes intuitive sense because if xi and xi plus 1 are close to each other, it is likely that the new value is probably similar to the old value. This equation provides a perfect estimate if the function being approximated is in fact a constant. However, if the function changes at all over the interval, additional terms of the Taylor series are required to provide a better estimate. For example, the first order approximation is developed by adding another term to yield the function of xi plus 1 is equals or congruent to the function of xi plus the first derivative of xi multiplied by xi plus 1 minus x sub I. The additional first order term consists of a slope, which is the first derivative of the function xi plus 1 multiplied by the distance between xi plus 1 and xi. Thus, the expression is now in the form of a straight line and is capable of predicting an increase or decrease of the function between xi and xi plus 1. Recalling, this equation is simply similar to y is equals to b plus mx. Although the above equation can predict a change, it is exact only for a straight line or linear trend. Therefore, a second order term is added to the series to capture some of the curvature that the function might exhibit. It will be function of xi plus 1 is equals to or congruent to the function of xi plus the first derivative of the function xi plus 1 minus xi plus the second derivative of the function xi all over 2 factorial multiplied by the difference of xi plus 1 and xi squared. In similar manner, additional terms can be included to develop the complete Taylor series expansion. It is often convenient to simplify the Taylor series by defining the step size as h equals to xi plus 1 minus x sub I. And express as the function of xi plus 1 is equals to the function of xi plus the first derivative of the function xi multiplied by xi plus 1 minus xi plus the second derivative of the function xi all over 2 factorial multiplied by the xi plus 1 minus xi squared plus, sometimes this is symboled as this function, so it can also be in this manner. So, the third derivative of the function xi over 3 factorial multiplied by xi plus 1 minus xi cubed plus so on and so forth until you reach the first derivative of the function xi all over n factorial multiplied by xi plus 1 minus xi raised to n plus the remainder r sub n. Simplifying this, you will also be able to have or to represent the function using the step size h this representation. But, you have to be careful ng pagsusulat ng h and ng n. So, continuation. Where the remainder term is expressed as r sub n plus 1 derivative of the function she. So, if I'm not mistaken, this is read as she all over n plus 1 factorial multiplied by xi plus 1 minus x sub I raised to n plus 1. Or simply, you can change this into h. She is a value of x that lies between xi plus 1 and xi plus 1. That is, for example, use 0 through fourth order Taylor series expansion to approximate the function. Function of x is equals to negative 0.1 x to the fourth minus 0.15 x cubed minus 0.5 x squared minus 0.25 x plus 1.2. From x sub I equals to 0 with a step size of 1, that is predict the function's value at xi plus 1 equals to 1. This is simply xi plus 1 minus xi equals to xi plus 1 minus 0 equals to 1. Meron tayong value ng ating xi plus 1 equal to 1 from the initial xi equals to 0. So, yun yung ating h. Because we are dealing with a known function, we can compute the values of the function of x between 0 and 1. So, meron tayo dito xi equals to 0 and xi plus 1 equals to 1. With this, substituting the values of x as 0, we will be able to get the value of 1.2 and substituting the value of xi plus 1, which is 1, to the function, we will be able to get the value of 0.2. The result shown in this figure indicates that the function starts at 0 equal to 1.2 and then curves downward to the function of 1 equals to 0.2. Thus, the true value that we are trying to predict is 0.2 value. So, ito yung ating 1.2 and this is our 0.2. Continuing, for example, the Taylor series approximation with n equals to 0 is the function xi plus 1 equal to or congruent to 1.2. As in figure 4.1, the zero order approximation is a constant. Using the formulation result in a truncation or error, true error equals to the true value minus approximation. E sub t is equals to true value is 0.2 and the approximation is 1.2 is equals to negative 1 at x equals to 1. So, for n equals to 1, the first derivative must be determined to evaluate x is equals to 0. The first derivative will be, balikan nyo na lang later yung equation. This will be the first derivative of the equation substituting 0 with x. So, we will be able to have the value of negative 0.25. Therefore, the first order approximation for the function xi plus 1 is equal to or congruent to 1.2 minus 0.25h. Saan to galing? So, this is from the function of I, first derivative, multiplied by h, which can be used to compute function of 1 equals to 0.95. Consequently, the approximation begins to capture the downward trajectory function in the form of a sloping straight line. This results in a reduction of the truncation error to true error. E sub t is equals to true value minus approximation. So, E sub t is equals to 0.2 minus 0.95, which is equals to negative 0.75. For n sub 2, the second derivative must be determined to evaluate that x is equals to 0. So, we have the value of negative 1. Therefore, the second order approximation will be the function xi plus 1 is equals to 1.2 minus 0.25 minus 0.5 h squared. So, resulta na to class nung ating negative 1 all over 2 factorial h squared, which can be used to calculate for the function at 1 equals to 0.45. The inclusion of the second derivative now adds some downward curvature, resulting in an improved estimate. The truncation error is reduced to true error. E sub t is equals to true value minus approximation, which results to negative 0.25. Additional terms would improve the approximation even more. In fact, the inclusion of the third and the fourth derivative results in exactly the same equation we started with, where the remainder term is 0. Because the fifth derivative of the fourth order polynomial is 0. Consequently, the Taylor series expansion to the fourth derivative yields the exact estimate at xi plus 1 equals to 1, which is equals to 0.2. Para mas maunawaan natin kung paano nga ba siya naging remainder 0 and nagkaroon ng value na 0.2, so let's try using Excel.